All right, page 59. So far, we've found the values of limits, or we found limits numerically by making a chart and graphically by looking at a picture of it or making our own picture of it. Now we're going to find limits analytically. Now, one method is not superior to another. Analytics is what we spend the most time on, but there's nothing wrong with finding a limit of a function by looking at its graph. There's nothing wrong with finding the limit of a function by making a table of values. Those are perfectly legitimate ways of doing it. Okay? We tend to like, well, I don't even know if the word like is right. We tend to use the analytical method more often because it's algebra based. And at this point in your life, you should be pretty good at algebra. Okay? And also, you got to remember a lot about calculus. Well, all of calculus was developed before graphing calculators existed. So with a halfway complicated function, it used to be really difficult to graph them precisely. To get a sketch, maybe not so much. You could figure out, you know what quadratics look like, you know what cubics look like. But getting a specific one was a fairly complicated process until graphing calculators came along. So analytically became the favored method because it was easier. It's now probably not the easiest way, but it's still the way that you're taught in college and what's on the AP test. I said the way. It's in section 1.2. You learned that the limit of f of x as x approaches c does not depend on the value of f at x equals c. At least that's what we tried to learn. Okay? It may happen, however, that the limit is precisely the value of the function when x equals c. In such cases, the limit can be evaluated by direct substitution. That is, in many cases, the limit of f of x as x approaches c equals the value of the function when x equals c. Such well-behaved functions are continuous at c. And like I've said, that's what you've studied for the most part up until now. All right? Graphs that once you put your pencil down, you could draw the entire graph without ever lifting your pencil back up, right? That's what we're talking about. Those kinds of functions, the limit as x approaches c and the value when x equals c are the same thing. And if that's the case, if we know for a fact that the limit of the function as x approaches c equals the value of the function when x equals c, then all you got to do is stick c in for x, simplify it. Not only have you found the value, you found the limit. So we tried to spend a couple days hammering you overhead with the fact that the limit of the function is not the value of the function. And now we're backing up and saying, well, sometimes it is. Okay? And when it is, and we're going to have theorems that tell us when it is, to find the limit involves the exact same thing as finding the value of the function, which means you substitute. Like, if you're trying to find f of 3, don't you just stick 3 in for x? So if we know for a fact that the limit as x approaches 3 is the value when x equals 3, to find the limit, then all you have to do is put 3 in for x. And then it's simplifying. All right? So, first theorem on page 59, some basic limits. Let b and c be real numbers, and let n be a positive integer. The limit of b as x approaches c equals b. The limit of a constant is that constant. So what's the limit of 7 as x approaches 2? 7. What's the limit of 14 as x approaches 9? 14. Why? Because graph that. If we're finding the limit of 7, that means 7 is our f of x. And the graph of f of x equals 7 is a horizontal line where the y-coordinate always equals 7, doesn't it? So the limit of a constant, think of what a constant function is. It's a horizontal line. the only y value that it ever approaches is that y value that's the horizontal line. So the limit of a constant is the constant. Now on this, though, that's just the line y equals x. The limit of x as x approaches c equals c. Because if that's our f of x, that's our graph of f of x, isn't it? So as x approaches 2, what's the y coordinate always approaching? 2. As x approaches negative 3, what's that y coordinate approaching? Negative 3. That's right. That's right. But since that's always what that means, that always transfers to that. Okay? So the limit of x as x approaches c is c. So what's the limit of x as x approaches 4? 4. What's the limit of x as x approaches negative 2/3? Negative 2/3. All right? Now, the limit of x to the n as x approaches c equals c to the n. I'm not going to draw this one because this could be a lot of different things. This could be quadratic or cubic or to the 4th, to the 5th. But you've dealt with these graphs in the past. Aren't they all continuous? They don't ever have any holes in them. They don't have any asymptotes. They're just nice, smooth graphs. I mean, some of them better looking than others. That's quadratic. That's cubic. And, of course, you can flip them with the negative, and you can make them wider or skinnier and all that. But so whatever the value of c is leads directly. So in other words, if we did a quadratic here, all right, and we said it was y equals x squared. Well, the limit of f of x equals x squared, as x approaches 2, wouldn't it just be 2 squared? And as x approaches 7, wouldn't it be 7 squared? Or if we dealt with the cubic graph, the limit of that cubic function as x approaches 3, wouldn't it be 3 cubed? As x approaches negative 15, wouldn't it be negative 15 cubed? Okay? So, does number 3 make sense? Now, I'm not actually going to do a formal proof. I try to make it make sense for you. Does it make sense? Now, look what that means. Look at 2 and 3 together. All I did to find the limit of x was replace x with c. All I did to find the limit of x with an exponent on it was replace x with c. So these two are telling you that linear functions and exponential functions can be evaluated by substituting the number c for x and then simplifying. Okay? All right. For instance, limit of 3 is 3. I don't care what x is approaching. The limit of x as x approaches negative 4 is negative 4. The limit of x squared as x approaches 2 is 2 squared, which is 4. You with me? All right. Let's see. Before I move to this, if I want the limit of 8, I don't know how, limit of 8 as x approaches 4, what do I get? 8. If I want the limit of x as x approaches negative 4/5, what's it equal? If I want the limit as x approaches 2 of x to the 5th, what's it equal? It equals 2 to the 5th, which we can then figure is 32, isn't it? 2 times 2 is 4 times 8. Yeah, 2 to the 5th, 32. All right, makes sense? All right. Now, here's another theorem with lots of properties. Lots of good properties. B and C are real numbers again. N is a positive integer, so we're not ready to deal with exponents that are negative or fractions. And let f and g be functions. And they tell us that the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is K. So for our first property is scalar multiple. If you have the limit of f of x times a constant, you can turn that into the limit of f of x times that constant. Okay? So for instance, if I'm trying to find the limit of 3x as x approaches 4, I can actually factor out that constant of 3 and make that 3 times the limit as x approaches 4 of x, which is 3 times 4, and I get 12. Couldn't I also have just left that whole and substituted a 4 in for x and ended up with the exact same thing? Yeah. Okay? So the scalar multiple property says two things. One, we can factor constants out and set them in front of the limit notation. And the rest of the problem works the way it's going to work. It's also telling us, hey, when you have just, well, I can call that a linear function, can't I? 3x is a linear function. When I have a linear function, I can just use substitution to find the limit. Number two, some are different. If we're finding the limit of two functions added together or subtracted together, just find the limit of the first one, find the limit of the second one, and then either add them or subtract them. Like this. If I had the limit of x plus 4 as x approaches 5, this property says I can write this as the limit of x as x approaches 5 plus the limit of 4 as x approaches 5. And we now know what the limit of x as x approaches 5 equals. It's 5. And we know what the limit of a constant is no matter what x is approaching. Could I have gotten this one just by substituting? Yeah. All right, our third one, the product. If we're finding the limit of two functions multiplied together, find each of their limits and multiply them together. So for instance, if I had the limit of, well, let's make it easy, x times x, because I know how to find both of those, don't I? As x approaches 3, this property says I can make this the limit of x as x approaches 3 times the limit of the other x as x approaches 3. What's the limit of x as x approaches 3? 3, 3, 9. Could I have gotten that right off the bat just using substitution? Yep. All right. Quotient rule. If you're trying to find the limit of one function divided by another function, make sure the bottom one's not 0. You can do that by finding the limit of the top one, the limit of the bottom one, and working it out. Like this. If I wanted to find the limit of 1 over x as x approaches 3, I can make this the limit as x approaches 3 of 1 over the limit as x approaches 3 of x. What's the limit of 1 no matter what x is approaching? What's the limit of x as x approaches 3? Couldn't I have gotten that real quickly just by substituting 3 in for x right off the bat? Yep. And the last one is the power property. If you have the limit of a function raised to an exponent, then that's just find the limit of the function and raise it to that exponent. Like this. If I have the limit as x approaches 2 of x to the third, I can think of it this way. Find the limit as x approaches 2 of x, and then raise it to the third. What is the limit of x as x approaches 2? 2. Couldn't I have gone straight from there to there just by using substitution? Works the same way. Yep. Huh? If it's got x in there in any way, then you actually have to work something out. All right, Alex? Scalar means a constant, whereas product, both of these can be variables. All right. Cool, huh?
That wasn't working here.
Gets better.
Actually, it did really good.
No, it gets better. All right. In example 2, which you can go back and look at here in a minute, note that the limit as x approaches 2 of the polynomial function simply turns out to be the value of that function when x equals 2. All right, and you can go back and look at it. It really does. Trust them. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators. This is big. Direct substitution is a valid method of finding the limit of any polynomial function. Every polynomial function in the world, you can find its limit as x approaches anything you want just by using substitution. Because polynomial functions are always continuous. They don't have holes, they don't have asymptotes, they don't have breaks, they don't have any of those things. Hang on. Rational functions don't either, as long as the denominator doesn't ever equal 0. Now, with rational functions, do denominators equal 0? Yes, sometimes. Like if your denominator is an x plus 2, then when x equals negative 2, your denominator is 0. Okay? But whenever the rational function does not have 0 as its denominator, you can use substitution to find its limit. Okay? All right, Charlie, question. Yep. Yep. Then we got an issue. If the denominator can equal 0, we'll have to work with that. Okay? All right, so what we're saying then, well, not yet, we're not. Then we look at this. Look, substitution works for radical functions. And substitution works, well, here's actually a little formula for a composite function. The limit of f of g of x, remember those composite functions, as x approaches c, is f of whatever the limit of g of x as x approaches c is. Okay? Then even more fun. You were wanting to get to trig, weren't you? Okay? Look, substitution works for all the 6 basic trig functions. What's the limit of x, or the limit of the sine of x as x approaches c? Whatever the sine of c equals. What's the limit of the cotangent of x as x approaches c? Whatever the cotangent of c equals. And so forth. Here's what we've been aiming at since we started this section. All the theorems we have so far mean that substituting c for x is a way, and in fact usually the best way, to evaluate the limit as long as f of c is defined. Well, yes, all of the above. Okay? So, even better, don't even write that. Write this down. Whenever direct substitution works, then it is a valid method to find the limit. Substitution. Okay? So, polynomial functions, rational functions, trig functions, radical functions, and combinations of them. Because our sum and difference rule and our product rule and quotient rule says that they work too. So any combination or composite made of polynomial functions, rational functions, radical functions, and trig functions, substitution will find your limit. The only exception is if it makes the function undefined. You cannot have, substitution does not work if it makes your denominator equal 0. Substitution does not work if it gives you a negative number under an even index radical like square root, fourth root, sixth root. Otherwise, it works. Now, we'll spend a lot of time on the otherwise. But right now, isn't that good to know? That when substitution works, use it. Okay? Let's see if we got time for an example. All right, turn to page 67. All right, on number 4, it says use a graphing utility to graph the function and visually estimate the limits. So we haven't gotten away from that. So I want my y to equal x. Oh, where do I find absolute value? Math. There it is. It's under, in mine at least, it's under math and then number. Absolute value of x minus 4. No. Then I'll graph that. All right, so what's the limit as as x approaches 4? 0, isn't it? And what's the limit? That's not for us. As x approaches -1. And since I don't really know, because I don't have I'm going to trace. Trace is a good thing. And in fact, well, I've turned trace on. So I'll just trace. And as x approaches -5, I must have this in wrong. X, oh, -1. Just back up a little bit. It's kind of hard to tell. So if I do zoom decimal, then it goes by tenths. So when I trace this, x approaches -1. Yeah, I get closer to -5 no matter which way I go. So -5. So no algebra involved. I could probably use algebra, couldn't I? But there we go. So don't forget the trace feature of your calculator. Oops. All right. Come on. Number 7. We want to find the limit. They don't tell us how. So let's do them analytically, because we need to get good at this. We have the limit of 2x minus 1 as x approaches 0. Should substitution work? Let's see if it does. Replace x with 0, so it's 2 times 0 minus 1. Well, yeah, so negative 1. Number 15. The limit as x approaches 1 of x minus 3 over x squared plus 4. Does substitution work? Let's see if it does. As long as we don't get 0 for our denominator, it works. So, 1 minus 3 over 1 squared plus 4. Negative 2 over 5. Negative 2/5. All right, number 25. Let's make it a little more complicated. F of x equals 4 minus x squared. G of x equals x plus 1. I got to hurry, so let's look at part, well, I think you can just get it by looking, can't you? A and B. Can't you do those? Substitution. You with me on A? You with me on B? Now, C. We had a theorem that said with a composite function, the theorem was the other way around. The limit of f of g of x was f of whatever the limit of g of x was. They've reversed the letters on this one. It's the limit of g of f of x. So it's g of whatever the limit of f of x is, which we just found over here. Right? So the limit of f of x as x approaches 1 is just f of 1, which is 3. Then you just got to find g of 3, which you've already done over here. I know I'm going too fast, but it's not a constant. Here's g of x. Uh-huh. All right. I didn't get as many examples as I wanted, but I still want you to do 1 through 36.